at least going. All right. So just to remind, exam Friday. All right. So again, it's over 7.1, which was the trig identity stuff, right? So again, these are with the verifying the trig identities. That's the big thing out of that section. Just to remind of some of the fundamental identities that you might use in those. Remember, we had the Pythagorean identities. Oops, forgot my squared. No, I guess I wrote that one backwards. Doesn't really matter. So your Pythagorean identities, that's the sine squared theta plus cosine squared theta equals 1. 1 plus tangent squared theta equals secant squared theta. 1 plus cotangent squared theta equals cosecant squared theta. Those are the three Pythagorean identities. Not only being able to recognize when you have them, and so that you can make your appropriate substitutions, you should recognize, kind of if you've manipulated the equation into something else, correct? Like, for example, if you see something like 1 minus cosine squared, you can replace it with sine squared. Right? That kind of thing. So being able to recognize manipulations of those things. We also used the first two of these, we used with that trig substitution stuff. You had that on the last quiz I think we took. Okay. Used in trig substitution. Okay. So remember those trig substitution things was in that particular section. So you had something like square root of 1 minus x squared. You would use which one? You had 1 minus x squared. So notice that these have the pluses in them, right?
For my sine.
The sine squared. Yep. So you want to let the x equal the sine, right? If you've got 1 plus x squared, you would use that's tangent, good. And if you had x squared minus 1, you would use secant, good. And then if you've got a different constant in here, for example, instead of a 1, if you had a 4, you know that you would use sine, right? But in order to get that 1 minus sine squared, what do I need to put in for a constant? A 2, right? Because I'll have to square the 2 to make it a 4, so that we can factor out the 4. All right, so being able to adjust with a constant on that. And you'll notice there are 3 of those at the bottom of the review sheet there. 19, 20, and 21 are examples of those. What other ones did we have for different identities? We had the even odd identities. What that means is that I'll just do it for those 3. Even odd identities just talk about what you can do with the negative sign on the inside of sine, cosine, tangent, cotangent, secant, cosecant. What do you do with the negative here? Take it out in front, right? Move it to the front. That's the property of the fact that the sine function is odd. It's also a property that your tangent function is odd. Cosine, however, is even, so cosine of negative x is just cosine of x. Good. Yep. Good. The co-functions just have to do with the complement idea. Pi over 2 minus x is the complement of x, if you think about them as angles, right? So if I have the sine of the complement, that's the same thing as the cosine of x. And it works vice versa as well. If you have cosine of the complement, and that's just the sine of x. And it works for the other two co-functions as well. Cotangent of the complement is just the tangent and vice versa. Cosecant of the complement is the secant. They come in those co-pairs, co-function pairs. So you have the matches for those as well. They also talk about those ratio identities, basically being able to rewrite everything in terms of sines and cosines. So just to remind, let's say we do one of these. It's on your review sheet, and I'll leave the other ones for you for the practice. So let's look at number 2 there. You've got 1 plus sine x over cosine x equals cosine x over 1 minus sine x. Now, usually our rule of thumb is to work with the more complicated side and make it look like the simpler side, right? They both look equally complicated to me, right? So I don't think it matters which one we work with. Which one would you rather work with? All right, sure, why not? The reason why I picked this one is I just remind about one of the techniques that we have. Not a lot we can do with the right-hand side right now as far as simplifying it the way it looks, correct? But when we see a 1 minus a sine or a 1 minus a cosine, or likewise if you saw a 1 plus sine or a 1 plus cosine, sorry. Remember when there was a little trick we could do to help us introduce squares and use one of our Pythagorean identities? What was the trick to do? That's why I wanted to do this one specifically. What can you multiply top and bottom by? Yeah, 1 plus sine. Good. 1 plus sine x. Remember, we kind of do that conjugate idea. Because why do we do that? When you multiply a plus b times a minus b, what do you get? Yeah, difference of squares, right? We get a difference of squares when we do that. Why is that helpful here? Well, when we do that multiplication, don't do the multiplication on top. Do the multiplication on the bottom. What do you get when you multiply on the bottom?
1 minus sine squared x.
Good. You get 1 minus sine squared x on bottom. And why does that help? What can you replace 1 minus sine squared with? Cosine squared x. Good. Oops. We just said cosine squared x, and I started rewriting the exact same thing over again. That's why we do that little conjugate trick. It creates a difference of squares. And in trig functions, we have identities that involve differences of squares, right? So if you've got 1 plus a trig function or 1 minus a trig function, and you can't think of something else, particularly that's sine or cosine, and you can't think of anything else to try that conjugate trick. Multiply top and bottom by the conjugate of it and see if that's simplifying and replacing with the Pythagorean identity might help. Because now what can we do? As our final step here, what can we do? Yeah, cancel out one of the cosines, and you get the left-hand side. Notice if you would have started with the left-hand side, you would have multiplied top and bottom by 1 minus sine x and did the same thing. Is that okay?
I can just go up just to show the identities.
Yeah. Notice that, pardon me, a couple of the other identities that are on the review sheet there involve either a sum or difference formula or a double angle formula or perhaps a half angle formula. And I'll write those down here in a second. But my guess is that if you see an identity that you're asked to verify that it involves a sum and difference formula or one of the other ones, you might want to start with that side and go ahead and make the substitution first and see what simplifying you can do. Just kind of that would be my suggestion. All right. All right. So let's talk a little bit about 7.2. 7.2 was your sum and difference formulas. We had sum and difference formulas for sine, cosine, and tangent. What was your sum and difference formula for sine? Good. Am I not writing things correctly today? And remember, the sign in the middle matches, right? When you do cosine, what do you get? Good. Notice for the cosine one, the sign in the middle flips, right? And finally for tangent.
Tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta.
Good. Oop. It's a sum or difference on the top. It's a product on the bottom. The sign in the middle is the same as it was originally on the top, and it flips on the bottom. Those were the three formulas that we had in that particular section. We spent a good deal of time deriving these two. I'm not going to expect you to go through the derivation again with those triangles. That was a lot of fun that day, I know. But we're not going to relive the moment. The moment is past. Darn it. I know. All right. So what types of problems might you be asked? Well, again, notice that if you look at the problems 4 and 5 on the review sheet there, you might be asked to verify an identity with a sum or a difference formula in it. Again, my suggestion would be pick the side that has the sum or difference formula in it and simplify it and see what happens. That would be my suggestion on that. We had ones where you were asked to calculate the exact value of an angle. In particular, if you were asked for, I'll leave the ones that are on there so you have those for practice, but maybe you had tangent of let's say 19 pi over 12, and you wanted to calculate that. You could also do this with a half angle formula, by the way, but if we wanted to do it with a sum or difference formula, remember what angle I always told you to use? pi over 4, right? Whether you want to write it as a sum or a difference, always use it as a pi over 4. And then figure out what the other piece of it is missing. Pi over 4 is how many pi over 12s? 3. So you need 16 more. 16 pi over 12 does the same thing as 4 pi over 3. Because you get 4 would cancel on top and bottom. So I can write that as pi over 4 plus 4 pi over 3. And then using our sum formula, we can rewrite it as tangent of pi over 4 plus tangent of 4 pi over 3 over 1 minus tangent of pi over 4 tangent of 4 pi over 3. And now we can calculate the exact values of each of those, right? The easy one there is tangent of pi over 4 is equal to what? 1. 4 pi over 3 is in quadrant 3. Yeah, it's down over there. So the tangent will be positive. Tangent of pi over 3 is root 3. Because it's sine over cosine. So the root 3 would be on the top. For the pi over 3 and the pi over 6 angles, it's either going to be root 3 or 1 over root 3. And it depends on does the sine have the root 3 in it, or does the cosine have the root 3 in it? For the pi over 3, the sine has the root 3 in it. So tangent of anything with a pi over 3 in it will be a root 3, a plus or minus. If it's a pi over 6, it'll be a 1 over root 3. So then on bottom we'll have 1 minus root 3. So that's one use of the sum and difference formulas that we did. If we look at number 9 on the review sheet, notice that those look like problems that we did back at the beginning of the semester where you're given information about the trig function of angles and you want information about other trig functions of the same angle. So make your reference triangles and all that stuff that gives you information that you need. Likewise, if we look at something like 14 or 15, I thought I changed 15. It's all right, doesn't matter. The process is the same. If you look at something like 14 or 15, the first thing you would want to do is apply your sum or think about those inside things as being an angle. So if you did another one like that, say you wanted to simplify sine of inverse cosine of 3x plus inverse tangent of 4 over x, doesn't really matter. The first thing we did was, remember, make each of those things on the inside an angle. And then rewrote these that way, right? And then we use triangles again, right? So we had cosine would be adjacent over hypotenuse. Tangent is opposite over adjacent. So in the first triangle, do 3x and 1 for the sides we can label. And for the second one, 4 and x for the sides we can label. That was a weak right triangle there, wasn't it? Then you can use your Pythagorean theorem to figure out the third side. We've done problems like that before, right? These are just with letters as opposed to numbers. That's literally, yes.
What if instead of it was plus tangent, what if it was minus? Would the 4 over x be negative?
You could do it that way. If it was a minus, I would just use your minus difference formula.
Okay, so
Yeah.
just the tangent would come out.
Yeah, the tangent. Just like that. Yep. So then the way we've written this is sine of alpha plus beta. So then you would write it as sine alpha cosine beta plus sine beta cosine alpha. Right? And then read your things off the triangle. What is sine of alpha in this case?
Root 1 minus 3x squared.
Yeah, 1 root 1 minus 9x squared. Cosine of beta is good. And then likewise, the next one will be 4 over root x squared plus 16 for the sine. And cosine of alpha is 3x. Is okay? Look familiar?
Do we need to simplify that?
No, you do not need to simplify that, though. Please don't. All right. The last thing that was also in this section was rewriting something as a sinusoid function, or just as a sinusoid, right, as a function of sine alone. That's like 12 and 13 there on your review sheet. So let's go through one of those. So let's say you were asked to rewrite 7 sine, it doesn't really matter the number, 13x minus 8 cosine of 13x as a function of sine alone. I'm making these up so that you have the other ones to practice. That's why I'm doing that. All right. So remember, we're trying to fit this as sine of alpha plus beta is the idea, right? The way this is supposed to look. It's supposed to remind you of your sum formula for sine. Well, if this is going to be the sum formula for sine, then my alpha must be something like 13x, right? I got to figure out what the beta is. Okay? So this part right here needs to be represented. Well, I have to make an adjustment with the number, but this part right here better would be representing cosine of beta, and this number right here better be representing sine of beta. Okay. So the way we handle that, remember, is we first multiply and divide by the square root of the sum of the squares of the coefficients that we have. We haven't changed anything. But remember, we want this coefficient in front to represent the cosine of an angle. The coefficient in front of the first term to represent the cosine of an angle. The coefficient in front of the second term needs to represent the sine of that same angle. right? So I'm thinking of the 7 as being the opposite, excuse me, the adjacent side, and the -8 as being the opposite side. I need to create the right triangle. I need that hypotenuse. That's why we're dividing up by the hypotenuse there. Okay. So basically what we're trying to do, if you think about it geometrically, if you like to think about it that way, put this off to the side. We're trying to create a triangle where your adjacent side is 7 and your opposite side is -8, like so. That make sense? Okay. And then this side here is your hypotenuse. 49 and 64 is what, 113? I did that right? No, it's not. Yeah, it is. My brain is not working this morning. Okay. So that's what we're trying to create. We're trying to create this triangle so that I have the same angle. Okay? So the angle we want is this one, right? The one down here. It needs to be in quadrant 4 because the cosine is positive and the sine is negative. I can use either inverse sine or inverse cosine to find my angle. I'm going to choose the one that can possibly give me an angle in quadrant 4. When I do inverse sine or inverse cosine, which one will give me an angle in quadrant 4? Inverse cosine is always between 0 and pi, right? 0 and pi, this way. That's 1 or 2. It's inverse sine that's either 1 or 4, right? So we'll do the angle you want is inverse sine of -8 over root 113. That's a calculator active thing. Make sure it's in radians. What do you get when you do inverse sine of -8 over square root of 113? It'll be negative, that I can tell you.
-0.852.
852? So what you said? Okay. All right, so going back up then and finishing off the problem. That one square root of 113 that we multiplied on top stays in front. That's the amplitude of the sinusoid. Again, your 13x is playing the role of one of your angles. And then the minus 0.852 is playing the role of your other one. And that's it. That's how you do that particular problem.
Can we do one more of those?
Sure. Are there questions on this one before we do another one?
I'm just kind of confused on where the 113 came from in the very end.
49 plus 64?
Oh, okay. All right.
Yeah. Yeah. I can do another one though. You want to see another one? Yeah. Okay. Let's do negative 15 sine of 7x minus 24 cosine of 7x. Oops, as a function of sine alone.
I have a question.
Yeah.
So does it matter whether or not you put like square root of 11, 13 like in the brackets or just the 7 squared plus -8 squared like at the top?
Oh, here? You
Yeah,
asked me,
no,
you asked me if I care if you simplify that?
no, like you see in the brackets where there's like sine 13x,
Yes.
like doesn't matter whether or not you put the 11, 13 now or like the side
This inside?
no up, like further up.
Here?
Yeah. Like, do you need to put that there or like 11, 13?
Okay, I don't think I'm understanding what you're asking
Is
me.
it okay if we simplify it?
Oh, you mean if you want to put 113 here?
Yeah.
Oh, yeah, you can look right. Yeah. I was just illustrating where it was coming from. If you want to write it as 113 to start with, that's fine. Sorry.
That's fine.
I told you I'm out of it this morning. So what do we do first here? Okay. And again, if you want to go ahead and simplify that at the time, that's fine. And then
Negative 15 over the just the root negative 15 squared.
yep, gotcha. And then that's times the sine 7x. And then likewise for the other one, right? That okay so far? And again, if you want to take the 225 and 576 and add them together, and not have to write out the mass, that's fine too. All right, so what's next then? Did the triangle help where the triangle was located? Okay. Where should I be drawing my triangle? What quadrant? Third, right? Notice that both the numbers are negative, right? So that means the cosine has to be negative and the sine has to be negative. So we're going to be down in quadrant 3 here. This, remember, in front of the sine has to be the cosine, and in front of the cosine has to be the sine, right? They're mixed when you're doing the sum formula for sine. So I'd have a negative 15 here and a negative 24 here for my sides. And then if I did my arithmetic correctly, this is square root of 801. I did it in my head, so the way my head's working today, I wouldn't trust that arithmetic. But 225, 200 plus 500 is 700, and 75 and 25 and 76 is 101. So it should be 801.
Yep.
It may not work the other ways, but at least I can still do arithmetic.
Can you explain one more time the negative 15, negative 24, how you put why you put them where they are on the triangle?
Okay, so the coefficient out in front of the cosine, out in front of the sine has to be the cosine. So that has to be the adjacent side. And then that has to be the sine, so that has to be the opposite side. That's where I'm getting those. Yep.
Okay, I see. So it's divided by the hypotenuse, like the hypotenuse.
Yep, exactly. It's divided by the hypotenuse. That's exactly right. That's how we're creating those. Yep. So where's it good? Okay. Pardon me. So then we need to figure out the angle. We need this angle down here, don't we? And then that moves around all the way, don't we? Again, you can use inverse sine or inverse cosine. It doesn't matter. In this case, since we're in quadrant 3, notice that your inverse cosine and your inverse sine don't fall in quadrant 3. Neither of them do they? Inverse cosine gets you up here. Inverse sine is around this way. How I would do it in quadrant 3 is ignore the negatives, get your number, and then add pi. Right? Because you can just think about this being a triangle that would have the same picture up here. So if I find that positive angle there, then I can just add pi to it. So use either inverse sine or inverse cosine. They'll both work. So your beta in this case would be pi plus inverse sine of 24 over square root of 801, or inverse cosine of 15 over 801. Either one will work. They'll give you the exact same number when you type them into your calculator. And again, the only reason why we've got the pi plus here is because we're in quadrant 3. And I actually want the positive angle here because I'm going to take pi and add that bit. That's why I'm not putting the negatives in there. Does that make sense? By the way, we're going to do this kind of stuff when we solve equations next week. We're going to do this again, which is why I'm working on it now too. Because it's going to come back again. Woo! What value did you get for those?
4.154.
Okay. So then how do we write our final function then? It'd be square root of 801 times sine of what?
7x plus 4.154.
Yep. And I'm writing equal. I guess I should mean approximately equal because the 4.154 is not the exact value, but forgive the abuse of notation. Mathematicians actually call it that if you use a notation poorly. Call it abusive notation.
So
Sounds negative, doesn't it?
you said you don't want us to simplify that number in the final equation, or you got 4.15.
I do want a decimal equivalent for that.
Okay.
I mean, technically, if you wanted to write this whole thing on the inside rather than typing your calculator, you could do that. I don't care. It tells me you know what you're doing. I just figure you probably didn't want to write all that again. But you can plug that right into the thing. That's okay? There's a couple more examples of it help. So that was all in section 7.2. I guess we have one more section to talk about, which is 7.3. 7.3 was double angle, half angle, and the product of sum formulas. So remember the double angle formula for sine is 2 sine theta cosine theta. For tangent, it's 2 tangent theta over 1 minus tangent squared theta. And we just had one standard formula we wrote for those. For cosine, we had 3 of them. This is why I'm doing it last. For each of the 3, we used the sum formula for each of them to get those formulas, right? We just wrote 2 theta as theta plus theta, and actually I think we did it with x's to start with, but the letter doesn't matter, right? So that was how we got these. These last 2 were just doing Pythagorean identity substitutions for either sine or cosine to get the other 2. Right? The half angle formulas, I typically write them, well, I'll write it this way. Rather than writing them as angle over 2, I prefer writing it as a double the angle on the inside. Oh, why am I writing X's? Sorry. Hold on. Remember again, why they're called half-angle formulas is because the input on the left-hand side of the equation is half of the input that you see on the right-hand side of the equation. That's why they're called the half-angle formulas. Remember also that this is not truly plus or minus. That's I have to make a decision, is it positive or is it negative, depending on what quadrant the input is here on the left-hand side. So if it's 1 or 2 on the left-hand side, you'd use the plus. If it's 3 or 4, you'd use the minus. Here, if it's 1 or 4, you would use the plus. If it's 2 or 3, you would use the minus. So again, I know I made a big deal about it the other day, but just to emphasize, it's not a true plus or minus. You have to make a decision. Is it the positive or is it the negative? You can't leave it as a plus or minus because then it wouldn't be a function. You'd be getting plug one thing in and get 2 things out. That's not a function. All right, and then we had the product of sum formulas. We had one that mixed the sine of alpha and the cosine of beta, and we had one that, or the other two, were either sine, sine, or cosine, cosine. They all 3 have a 1/2 in front. The first one is sine of alpha plus beta, and then plus sine of alpha minus beta. The second one here is cosine of alpha plus beta, and then it should be a plus cosine of alpha minus beta. The other one is reversed and subtracted. I don't have a real good way to remember the last one. The first ones, I think, kind of makes sense of what the form has to be. I'm trying to get sine alpha cosine beta, or I'm trying to get cosine alpha cosine beta, which is the first half of the sum formulas for sine or cosine, depending on which one you're looking at, right? Yeah. So I think this kind of makes sense that you want sine alpha plus beta or cosine alpha plus beta as your first term here. We're going to add on the exact same thing on the other side, but we want to use the opposite sign so it cancels off the part that you don't want. So I think those two mirror each other, and it's not too hard to remember what they are. And as you're adding them together, you get 2 of them, so I need to do a half out in front. You can't make sure that everything's equal. The last one, you're trying to pick off the second half of the equation rather than the first. So in my brain, it says, oh, I need to flip them around because I need to get the second half rather than the first. So I flip it around. I'm not sure that's necessarily helpful. I'm just trying to think of ways that may be a little bit easier for you to remember what the formulas are, because there's about 18,000 formulas in this section. So the main reason why we use those last ones, and you've got some other problems, half-angle formulas. You can use the half-angle formula to do ones we've done where we've done the sum of the angles, anytime you've got a pi over 12, you could use a half angle formula instead of the sum or difference formula. But if you've got a pi over 8, you'd have to use the half angle formula. So, for example, if you wanted cosine of 9 pi, let's do 11 pi over 8, then that is either plus or minus square root of 1 plus cosine of 11 pi over 4 over 2. Again, inside here is half of what's inside here. Calculate cosine of 11 pi over 4. Cosine of pi over 4 is root 2 over 2. 8 pi over 4, 9, 10, 11 pi over 4 is in quadrant 2. Right? It's always weird to me when I'm teaching because I have to do it backwards. Right? Okay, anyway, doesn't matter. So this will be negative root 2 over 2 over 2. And then you have to decide, do I want the positive or do I want the negative? Well, where is 11 pi over 8? That's 8 pi over 8. Right, halfway around is 8 pi over 8. Down here would be 12 pi over 8. So it must be in quadrant 3. So I'd use the negative, right? So my final answer would have a negative in it. Again, where do I look for the negative? The negative doesn't come from here. The negative comes from where that angle is. These two things are going to be in different quadrants, typically. Okay. Does that make sense? And then just to do one with a product or sum formula, just so we have one that looks like examples from 16, 17, and 18. If you're asked to rewrite, let's say, sine of 13x, cosine of 8x as a sum. This is just a straight application of the first equation, right? That we had. So what goes inside the first sine function?
Thirteen plus 13x
13x plus 8x, so you have 21x there, right? And then plus sine of 5x, yep. It would be 13x minus the 8x, yep. Questions on that one at all? Again, looking at the review sheet, not going to be a huge surprise with the types of problems I'm going to ask. There will not be 21 problems on the exam by any stretch of the imagination, but you can see the types of problems I'll ask. Okay. This is already posted on Google as well as answers. Should be up there. If not, they'll be up there this afternoon. I'm pretty sure I already posted it. But like I said, my brain is fried today. Apparently, I can't guarantee that. Anyway, we'll see you on Friday, if not before. You can always stop by if you've got questions about things that you want to ask questions before the exam as well. So have a good one, everybody.